At the end of the last video, we learned important velocity fact number 1. A body is at rest when its velocity is 0. Here we have important velocity fact number 2, sort of a collection of facts. When velocity is positive, motion is forward. We said in the last video, velocity is speed with direction. So speed, and then am I moving forward? Am I moving backward? So velocity, when velocity is positive, motion is forward. So you may guess that when velocity is negative, motion is backward, whatever forward and backward meet in the context. And then, therefore, direction from forward to backward or backward to forward, direction changes when velocity changes sign. So try this example. Here I have a graph of velocity, v of t. Notice we have to know this is velocity. A particle moves along the x-axis with this velocity. Velocity is a function of time, shown here in this graph. At what time does the particle change direction? Well, I would say, if this was the free response section, I think this is actually a released free response problem, I would write this out in words. I would say the particle changes direction at time 3 and time 5 because velocity changes sign at those values. So we have to make sure we understand really deeply what we mean by changing sign. Notice in this section of the graph, the velocity is positive. I can tell that because the velocity is above the input axis. And in these sections, velocity is negative because the output values, the v values, are below the input axis. So again, direction changes. The particle changes direction at time 3 and time 5 because velocity changes sign, S-I-G-N, sign at those times. All right, at the top of the back page there, acceleration is the derivative of velocity. If you try to explain how velocity is changing, what you're talking about is acceleration. So that's instantaneous rate of change. How does velocity change? That's acceleration. So if a of t is what we're going to use to stand for the acceleration function, that's the same as dv dt, or the second derivative of position, we say d squared s dt squared. Or if you want to use this function notation instead, a of t is v prime of t, which is the same as s double prime of t. So a released multiple choice question. The position of a particle moving in a straight line at any time t is given by this position function, t squared plus 4t plus 4. Find the acceleration of the particle at time 4. So how am I going to find the acceleration? I know the position function. I'm going to have to find the acceleration. That's going to take 2 derivatives. I need to find the second derivative of position. That will be my acceleration function, and then I'll evaluate my acceleration function at time t equals 4. All right. So I said here, solution, find a formula for a of t, which requires a second derivative, and use that formula to compute a of 4. So I'm following along here. The velocity is the first derivative of position. So I know how to take the derivative of this polynomial function. S prime is going to be 2t plus 4. To find acceleration, I'm going to need to take the derivative of that function, the derivative of the velocity, which is 2. I'm looking at that number 2 was the derivative of 2t, the derivative of 4 is 0. So if I have my whole acceleration function is right here, 2. So that's interesting, that's a constant function. Notice it doesn't even depend on the input value. So a of t is 2, no matter what the t value is. So when I find a of 4, that's also equal to 2. So just a note here, we want to be able to understand the relationship between a position graph, the velocity graph associated with it, and the acceleration graph. We spent a lot more time on this in chapter 4, but we want to plant some seeds here because I guarantee you, I would bet you $100 that on the free response section of your AP test, there will be a question about velocity, acceleration, and position. So let me just scoot this up here a little. Okay, so remembering that slope means, derivative means slope, And instantaneous rate of change means slope, means derivative. And we've said already that the derivative of position is velocity. So it's like the slope of the position function is velocity. So just notice here, if I have a graph here of the distance function, anytime the distance function goes uphill, so the real way to say that, anytime the distance function is increasing, the slope of the distance function is positive, which means the velocity must be positive. So notice here I have an uphill position function, which means velocity is positive, velocity is positive, velocity is positive. Any place I have a decreasing position function, I have negative velocity. Negative velocity, negative velocity, negative velocity, because my position function is headed downhill. Here, my position function is flat. So what's the slope of a horizontal line? 0. So I have velocity 0. Recall then that acceleration is the derivative of velocity. So we're going to think about the slope of this function and think about how that slope is changing to think about acceleration. I'm going to start here with this little piece of the graph. My slope is positive, so I know that velocity is positive, distance is increasing. But notice this piece looks linear, which means the slope is constant. So that's why we said here velocity is positive, because distance is going uphill as distance is increasing, and constant because it's not like it was getting more increasing or less increasing. It's increasing at a steady rate. So here we have a velocity that is constant, which means the slope of the velocity has to be 0. Look at this section here. We already said that the velocity is positive because this function is increasing. But check this out. As time goes on, this function goes uphill and then goes even more steeply uphill. That means the velocity is increasing, which means the derivative of velocity must be positive. Well, the derivative of velocity is acceleration. So that's how we decide here that the acceleration is positive. In this section, distance is increasing, so velocity is positive. We already said that. But it's positive, but it's not getting more steeply positive. In fact, it kind of feels like it's about to flatten out. So the velocity here is decreasing, which means the acceleration will be negative. So I'll just point out here, we're going to spend a lot of time on this in chapter 4. But this part of the graph, acceleration is negative for that whole section of the graph that I just circled. And just notice how that makes like a sort of an upside down, looks like an umbrella, right? So we're going to talk about how that relates to the concavity of the graph. You've discussed concavity in one of your other classes. That's what's going on here. Turns out the second derivative of a function tells us about its concavity. So just planting a seed for the future. Here, again, we have another piece that seems linear, which means the velocity is negative, but constant. It's not getting more and more negative. It's the same negative velocity. Well, if it's a constant, then its derivative is 0. So that's what I have here, acceleration 0. Move me out of the way. I especially want to talk about this last little piece. We said here that the velocity was 0 because the distance function is flat. So the derivative of, the slope of a horizontal line is 0. So then the derivative of 0 is also 0. So we have acceleration of 0 here as well.